Continue with the multiplication rule. We want to think about a poker deck, a standard 52 card poker deck, which is the kind of card deck you think of when you think of cards for most people. You're going to randomly select 2 cards, right, with replacement after each draw. So how large is the sample space? And the answer is 52 times 52, right? Because there's 52 cards for the first option, then there's 52 cards for the second option. So 52 times 52 makes 2704. Now, are the outcomes equally likely? Well, that's a different question. The answer is yes, right? Because we replaced the cards, then every outcome has just as likely a chance as anything else, right? All the way along. All right, now let's find the probability that the first card is a spade and the second card is a heart. So that means that I need the first card, spade, so I need probability of spade times second card, heart, probability of heart. Now you can do this 2 ways. You can think, well, there's 13 spades out of 52 cards total in the deck, and there's 13 hearts, so I can multiply 13 times 13. That gets me this. That's an unreduced fraction, right? Or I could say, well, oh, and that reduces to that as a decimal. Or I could say, okay, look, I know that spades make up a fourth of the deck, hearts make up a fourth of the deck. A fourth times a fourth makes 1/16, so that gets me that as a decimal. Either way, it's the same answer. It's just a question of how you think of it. Okay? All right, now what a probability that they're both aces. Now, I wanted to make a comment, and I should have made a comment way back here. Well, let me find it. There it is. All right, so right after independent, down at the bottom of this page, when we learned about independent events and the and thing, I wanted to make a note to ourselves right here that the word and is often hidden, or actually gets hidden as well, but and's especially bad. And, which is what you need for this multiplication rule, is often hidden in words like both, all, twice, two, I want 2 aces, I want 3 hearts, that kind of thing. I want 2 aces in a club, that kind of thing. So the word and gets hidden inside the problem. Okay, so make a special note of that for yourself. Maybe I'll add it to the notes for you for later. All right. So now we go back here. What am I talking about? Well, I'm talking about it for this problem right here, because it says, there we go, it says it wants both to be aces, both, and I underlined the both. Well, if you want both to be aces, then you need the first one to be an ace and the second one to be an ace, right? So I need first ace and second ace right here. First ace and second ace. So I need the probability of ace times the probability of ace. Now remember, that's really the probability of ace squared, if you want to do it that way. Whichever way you want, I don't really care. All right, so I need 4 aces out of 52 times 4 out of 52, which is the same thing as 4 out of 52 squared, which gets you this as an unreduced fraction. Or if you think to yourself, oh, I know there's 1 ace in every 13 cards, because there's 13 cards in a suit. So 1 out of 13 times 1 out of 13, that's 1 out of 13 squared, so that's 1/169. That would also work. Both of the decimals come up to 0.2704. And now you can see why a lot of the time we work with decimals, because it's just easier and simpler. All right, now the great thing about this concept is that we can expand it to even more cards. So what if I was taking 3 cards from a deck with replacement? Again, we're not working without replacement in section 5.3 because it's more complicated. Remember, our multiplication rule that we have right now, way back here, is only for independent events. In order to ensure independence, we have to have that replacement piece. If we don't have the replacement piece, we're working with the general multiplication rule, not the one for independent events. All right, so how large is the sample space now with 3 cards? Well, that's 52 times 52 times 52, which is 140,608. All right, now we want to find the probability that all 3 cards were aces. And again, I underlined that because that all 3 business, that's really and. They don't come right out and say it, but you need the first card to be an ace and the second card to be an ace and the third card to be an ace. So that's ace times ace times ace, which is the probability of ace cubed. Now you can think of this 2 ways. You can think, oh, that's 4 out of 52 times itself 3 times, or 4 out of 52 cubed. Or you can think that's 1 out of 13 times 1 out of 13, right? Times 1 out of 13. So either way, you get a fraction and then you get a decimal. Now, I'm just getting these with a calculator or with Excel. It's, whichever, right? The decimal is way more useful and your calculator comes up with those, okay? All right, so now we've seen the multiplication rule for something like that, where everything was equally likely. Let's do something where they're not all equally likely. Now, we have the free throw percentage for any NBA player is 77%, i.e. the chances they will shoot a successful free throw. I can't ever say that right. You're going to randomly select 3 random independent NBA players and have each of them shoot a free throw. Now, I get this number actually from NBA data. And it's kind of the average, NBA players on average are about 77%. That's what makes them NBA players. My average is more like 17%, say, or lower. All right, so for each player, how many random outcomes are possible and what is the associated probability of each? So for each player, there's 2 possible outcomes. They could succeed, i.e. make the basket, and the probability of that is 0.77. Or they could fail. Probability of failure is 0.23. Now remember, a free throw is when, if you're not familiar with basketball that much, it's there's a box in front of the hoop, and if you stand at the line at the edge of that box and make a shot, it's sort of like a penalty kick in football, or I'm just trying to think. It's if you ever watch basketball, when players get fouled, if somebody knocks them over or something like that, they get to make a free shot, a free throw, or 2 or 3 of them depending on the severity of the problem. All right, so in probability we'll often use S for success and F for failure for obvious reasons, because it makes our lives easier. Now, how large is the sample space? Well, you think, okay, the first player has 2 options, right? So 2 times the second player has 2 options, 2, and the third player has 2 options, 2. So 2 times 2 times 2 makes 8. Right? All right, so using a tree diagram, construct the sample space of all possible outcomes. Use S and F. And here you go. Right? It should look very familiar, because it's pretty much identical to the one we made for genders before. So success, failure, and so on. So it gives you the options of success, 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 failure, success, failure, success, and so on, all the way down to FFF, fail, fail, fail. All right, explain why the outcomes listed in the sample space are not all equally likely, because they're not. And it's because the probability of success is 77% and the probability of failure is 23%. They're not equal. They're not 50-50. Back when we were first learning tree diagrams, way back here, we already did this tree diagram before. See it? And this one was everything was equally likely because male and female were assumed to be 50-50 shot. But down here, we're not assuming that. I mean, it would be a pretty crummy NBA player that has a 50-50 shot of making a free throw, right? And I know what you're thinking. Shaquille O'Neal. Yes, Shaquille O'Neal was notoriously bad at free throws. And he, or maybe you're not thinking that, but I'll tell you, Shaquille O'Neal was very bad at free throws. So he was actually around 50% for his lifetime average. His highest seasons got up into the high 50s. His low seasons were in the high 40s. But he's very unusual for free throws. All right, now, there's the tree diagram to help us. There's the sample space over there. They're not equally likely. The ones that have more S's should be more likely because success is more likely, right? All right, now we're going to use the multiplication rule and we're going to do it with Excel. So that's part of our Excel technology thing. So I'm going to go over here. So success, success, success. That's the probability of success times the probability of success times the probability of success. Now what I did to make my life easier was I actually put probability of success and failure over here just for my own benefit. And that way when I want to do this, I can say, okay, look, I want F1 to the 3rd power, right? Because I want to take success, success, success. 0.77 times 0.77 times 0.77. The next one, I want success, success, fail. So I need 0.77, which is F1, times 0.77, which is F1, times 0.23, which is F2. The next one, I want success, fail, success. So that's 0.77 times 0.23 times 0.77, and so on. This one is 1 success, 2 failures, so that's 0.77 times 0.23 times 0.23. And you keep going all the way down. until you get to the last one, which has to be fail, fail, fail. So that's 0.23, 0.23, 0.23. And again, if you have it kind of written out in cell referencing, it kind of makes things easier. That way, in case I wanted to change it, suppose I was Shaquille O'Neal and I only had a 57% chance, right, and a 43% chance, everything would automatically get calculated for me. Groovy, huh? But we have 77 and 23. So there are the probabilities, all figured out with Excel on our technology sheet. So I'm going to go back. There they are. I pasted them in. So what are the chances of success, success, success? It's right here, 0.46533, right? It's this one right here. I'll even highlight it for you. There we go. Right, that guy is that one. Now what about success, success, fail? That's this one right here, right? I'll put it in green. Right? So you want the first two to be successful, the third player to fail. That's success, success on the first two, fail on the second one, or the third one, excuse me. What about this one? The probability that two succeed and the third fails, but it's not in order. So be careful. I guess I should say this, and one fails. Let's put it that way. Well, that's a totally different question than the other one, right? I'm not asking for the first two to be successful and the third one to fail. I'm saying I just want two successes and a failure. Okay, well, I'm going to go do that in Excel real quick. So I want two successes and one failure, but not in order. So what that is that's the probability of, let me put it this way, it's the probability of success, success, fail, or success, fail, success, or fail, success, success. So what I'm going to do is I'm going to add up those probabilities. So this one right here, plus this one right here, success, fail, success, plus that purple one right there, fail, success, success. There's 3.136s, and it's those three added together. That's your probability. And that was for part, better check it, for part H. Oops. Stop that. There we go. So there we go. For part H, that's our answer. I'm going to highlight it for my own benefit. Alrighty. So back here, that's where this guy comes from, right there. Right? And it's by taking that green one and this one right here and this one right here and adding them up. And again, you don't need Excel to do it. I'm just using Excel because Excel is available to me for nothing. And it helps figure out difficult things really quickly and easily. So if you haven't noticed it, the wording on these problems is really important to you because how things are worded really affects what the answer is. These answers are totally different from each other, right? And you have to be able to spot the differences in how things are written to be able to do it. Okay? So it's tricky, I know, but it's true. All right. I think we're done with that. And next time I see you, we will compute at least probabilities. But we are done with the basics of the multiplication rule. And we've seen how powerful it is and how useful it can be. And we've seen that we have to be careful with how things are worded. Because how the instructor writes the question will really change what your answer is going to be. All right, I'll see you back here for at least probabilities in the next video.